The first concept we're going to be looking at is that of the transformations of functions. There are three main types of transformations of functions. The first type is translations. A translation is a change in position of the graph of a function as a result of an addition or subtraction at either the input level, which we usually refer to as x, or the output level, which we usually refer to as y, in the definition of the original function. Translations can move a graph up, down, left, or right. Translations do not change the shape of the graph of a function. That's important to remember. And this is what we were referring to in our last video when we did the proof of the fact that perpendicular lines have negative reciprocal slopes. Remember that we explained that we can use translations to move the two lines so that their point of intersection will coincide with the origin. Next, we have dilations. A dilation is a stretching or a shrinking about an axis as a result of a multiplication or division either at the input level, the x level, or the output level in the definition of the original function. Dilations can and often do change the shape of the graph of a function, so keep that in mind. Reflections are more like translations in that they don't really change the shape of the graph of a function. A reflection is a mirror image of a graph of a function across a line of reflection as a result of a multiplication by -1 at either the input level x or the output level y in the definition of the original function. In a matter, as I said, similar to translations, reflections do not in themselves change the shape of the graph of a function. We'll take a look at these visually and bring them to life as we go through this lesson. Okay, in this first screen, we're going to look at translations. Assume that we have a function f of x and let k be a positive real number, and we want to see how we can obtain the graph of these alterations of f by just shifting the graph either left, right, up, or down. So if we want to graph a f of x plus k, remember k here is a positive number, all we're going to do is take the graph of the original function f, which I'm depicting here using a dotted line, and to obtain the graph of f of x plus k, we're just going to shift it k units up. That's all we do. And this is called an upward vertical translation. So take any graph, as long as you're adding k to the entire f of x or the y value, you're basically increasing all the y values by 3. Okay? You want to shift the graph down k units, just look at f of x minus k. So this is called a downward vertical translation. Basically, you're reducing all the y values of each ordered pair on the graph by k units, actually, like so. Okay, well, here I think I'm looking at this example, which is giving me the notion of 3. All right, now if you want to shift the graph left or right, you're going to be acting on the input level, right? We're going to bring a difference at the input level. Notice that these two, you're making a change to the output or f of x or y level, right? So if you want to bring about a change, a horizontal change as far as a translation is concerned, you're going to make an alteration to the input. So instead of f of x, if we look at f of x minus k, that is just going to require a shifting of the graph of the original function f of x k units to the right. Now remember, even though that's a minus, a lot of people think minus left. No, that actually ends up being a rightward horizontal translation. Basically, think of it like whatever is happening here is going to happen to this graph k units later. Okay, so if this one hits a 0 here, f of x minus k is going to hit the 0 height k units later. Okay, how about f of x plus k? Well, that does the exact opposite, right? This one, whatever happens to the original function happens to this function k units earlier. So that's why that's an actual horizontal translation to the left, or a leftward horizontal translation. All right, so they all make sense. Make sure that you understand them, because trying just to memorize these, it's going to be too many concepts, too confusing. But if you understand them, there's very little that you would need to memorize. Basically, in general, what has to happen is you have to shift your focus from just remembering things to understanding things. Then remembering follows understanding like a shadow. Okay, unfortunately, because understanding is the real thing, it doesn't work the other way around, right? You can't expect to memorize and have understanding follow it like a shadow. Just like a shadow can't make a real object follow it, right? It always has to work the other way around. So make sure that you understand, and do not worry so much about remembering, because if you understand, you will remember. Always have confidence in that fact, because it's the truth. Okay? All right, let's go ahead and look at some other transformations. All right, the next group of transformations we're going to look at do change the shape of a graph. The general term for this kind of transformation is a dilation. Even though when you think of dilation, you always think of a stretching, but it's also the general term that handles shrinking and stretches, both stretches and compressions. Okay, so with these, you need to be slightly careful just because of the fact that the shape is changing. So you need to understand how the shapes are going to change. If you recall on the last slide, which is what I'm showing you right now, the shape does not change at all, right? Notice the shape does not change under translations. Here, however, notice the shape is changing. This one is becoming thinner. This one is becoming wider, etc. So what if we have a function f of x, and again we have a constant k which is positive? What will we need to do to the graph of f of x? Notice f of x here is being drawn as the dotted graph, right? Or the dashed graph. So what will we need to do to that reference function, right, in order to obtain the graph of this function? Now notice here we're applying we're multiplying k by the f of x, or the y value, so by the output, right? So basically all the y values are going to be multiplied by some number. Now as long as that number is greater than 1, what's going to happen? You're going to go, for each x value, you're going to get a higher y value. So this is what we call a vertical stretch, right? Notice the stretch is vertical. Now that is often associated with a simultaneous horizontal what? Shrinking, right? So, but the main thing to focus about is the direct action that's happening, which is a vertical stretch, okay? Now, if the value of k happens to be between 0 and 1, then what's going to happen is, for example, if you multiply the y value by a half, then all the y values for that are going to get halved, right? So what's going to happen? Vertically, these y values are going to get smaller and smaller, right, compared to those. So, well, at a fixed rate of, whatever it is you're multiplying by. So notice that that's going to result in a vertical compression, right? Vertical compression. So like this. But notice a vertical compression is associated with a horizontal what? Stretch. So these kind of go hand in hand. All right. Now, if we take the original function and multiply k at the input level, right? And k is between 0 and 1, like for example f of 1/2 x, etc., then what's going to happen is you're going to horizontally stretch f of x by a factor of 1 over k. Now, this obviously is called a horizontal stretch or horizontal dilation. Note that a point xy on the graph of f would correspond to a point x over ky on the graph of f of kx, okay? And finally, if we act again on the input x and multiply it by k, and k happens to be greater than 1, right? This time we're going to horizontally compress the graph by a factor of 1 over k. And this obviously is called a horizontal compression or shrinking, all right? And again, we've seen this relationship that we were discussing. Okay, let's see some of this stuff in actual action. Just a little bit more of our general facts. We'll finish with the last type that we discussed, which was reflections. Remember, reflections, like translations, do not change the shape, but there needs to be a mirroring across some mirror, right? So if I'm dealing with a function f of x and I have its graph, let's say right there in the dashed format, right? If I want to graph g of x, which is the opposite of f of x, here I'm changing the y values, right, to the opposite. So basically, this is going to reflect this graph across the x-axis, right? And notice that if xy is on the graph of f, that implies that x negative y is on the graph of negative f of x. So this is why this flipping happens, right? It's a vertical flip, which is a formally called a vertical reflection. Now, if I want to graph f of negative x, now this time I'm multiplying the -1 by the input. So what's going to happen is there's going to be a reflection across the y-axis, right? Like so. Now, xy being on the graph of f is going to imply that negative xy is going to be on the graph of negative x, f of negative x, okay? And there's one other type of reflection, which is called reflection across the origin, which is across the point 0, 0. And that would give you the graph of g of x equals negative f of negative x. And notice that if xy is on the graph of f, then the order pair negative x, negative y is going to be on the graph of negative f of negative x. Okay, so these are the three kinds of reflections. Now, next I want to show you what the actual mechanism of reflection is and how to actually do it. Okay, so most generally speaking, whenever you want to reflect a point across a given line, what you're going to do is you're going to drop a perpendicular. This is the point P. We want to reflect it across this mirror, right? This line right here, L. So what we do is we drop a perpendicular to L, and then we continue moving in the other side of L, which is the side not containing P, in the same amount that we had to go from the point P to reach the point of perpendicularity on L, right? So we continue the same amount and then we stop and put a dot. There is the mirror image, right? So this is the reflection of the point P across the line L. Okay, so this is generally how you reflect across a line. Now, if you want to reflect an entire graph across a given line, basically reflect each point on that graph across that line using the same mechanism. Okay? Now, to reflect the point across the x-axis, you have to understand that the reflection of the point xy across the x-axis is just going to be the point x negative y, because remember, you drop a perpendicular and go the same distance to the other side. Where are you going to end up? Well, this was y, so you have to go to negative y, right? So this is consistent with the general reflection about a line that we looked at in the last screen. Now, if you want to reflect an entire graph across the x-axis, then simply reflect each point of the graph across the x-axis. Now, to reflect the point across the y-axis, what we need to understand is that the reflection of a point p of xy across the y-axis is just going to be the point p prime of negative xy, right? So here, you're just going to be dropping a perpendicular, moving the same distance around. So this distance here was x, so you have to go to negative x here. If you want to reflect an entire graph across the y-axis, then you're going to reflect each point on the graph across the y-axis. So, typo here. All right. Finally, to reflect the point across the origin, you have to understand that the reflection of a point p of xy across the origin is just going to be p of negative x negative y. So we're going to change both x and y to negative x and negative y, and that will be our reflection. Now, if you want to reflect an entire graph across the origin, right, then reflect each point on the graph across the origin. Here's a quick reminder of the commonly encountered functions we studied in the last lecture. We had the, remember, identity function, or, well, this is a general linear function. The identity function would be the line y equals x that looks like that. But generally, a linear function has the form f of x equals mx plus b. Then we have the squaring function, the cubing function. We have the reciprocal function, the absolute value function, the square root function, the cube root function, and the greatest integer function, which is also known as the floor function. Now, if I actually do look at replace the general f of x equals mx plus b with y equals x or f of x equals x, then these would all serve as the reference graphs that we're going to be applying transformations to. Okay, so keep that in mind. All right, so for our first example, we're going to graph g of x equals quantity x minus 3 squared and h of x equals quantity x plus 3 squared in the same Cartesian coordinate system by applying transformations to the applicable base or reference function. Name and graph the base function in a shaded manner, okay? So here the base function is going to be x squared, right? F of x equals x squared. So to obtain the graph of g of x equals quantity x minus 3 squared, remember, that's going to be f of x minus 3. So we're going to be moving the graph of x squared 3 units to the right, okay? So this right here in green is going to be the graph of quantity x minus 3 squared. We've taken, imagine this is made of a piece of wire, right? You're just picking it up and moving it 3 units to the right, okay? To get the graph of quantity x plus 3 squared, what we're going to do is we're going to take the graph of f of x equals x squared and just move it 3 units to the left. That's all we have to do. All right, in this next one, we're going to be doing some vertical translations. So to get the graph of x squared plus 3 and x squared minus 3, we start with the graph of x squared, which is shown here shaded, right? To get the graph of x squared plus 3, we're just going to pick that up, move it up 3 units, okay? And to get the graph of h of x equals x squared minus 3, we're just going to pick up the graph of x squared and move it down 3 units. Those are vertical translations. They do not change the shape of a function, or the graph of a function rather. All right, so here with this one, we're going to do a few transformations on the reference function x squared. Now, there are different orders in which you could do it, but the easiest thing is to work on the innermost part first. That's kind of consistent with the order of operations. So what we'll do is we'll take care of this business of x minus 3 squared. So we'll shift the graph of f of x equals x squared. We're going to move the graph of f of x squared 3 units to the right because it's x minus 3. Then we're going to move it 4 units down, and we're going to vertically stretch it by a factor of 2. And that's how we end up with this. So notice we took this, moved it 3 units to the right, then moved the whole thing 4 units down, and then we vertically stretched it, which notice it looks like a horizontal compression, right? And as you know, that's the case. They go hand in hand. So, but what we really cared about was a vertical compression, right? And that was by a factor of 2. Now, once we moved it 3 units to the right, we could have done the vertical stretch first and then moved it down 4 units. You still get the same graph, okay? All right, so here g of x equals 1/2 absolute x plus 3, right? Notice that our reference function or base function, which I'm calling here, is f of x equals absolute value of x. So to get from absolute value of x to this function, you have to take 1/2 of f of x and add 3, right? So basically, we're going to shift the graph of absolute x 3 units up, and then we need to take care of the 1/2, so we're going to vertically compress it by a factor of 1/2, okay? So again, notice that the vertical compression, this is the original graph of the base function or the reference function. This is vertically compressed compared to this, and notice how that corresponds to a horizontal stretch, okay? All right, so here we have g of x equals absolute value of 2x minus 4. We know that the reference function is absolute x. We want to see what relationship it has with this function. Notice that we can write g of x as absolute 2x minus 4 and factor out the 2, and we get 2 times the absolute value of x minus 2. And basically, we're dealing with 2 times f of x minus 2. Because if f of x is absolute x, what's f of x minus 2? Absolute x minus 2. So this is just 2 times f of x minus 2. Now we know that to get the graph of 2 times f of x minus 2 from the graph of f, what we have to do, here's f itself, right? The reference function. We have to move it 2 units to the right, right? And then we're going to vertically stretch it by a factor of 2. Again, a vertical stretch will come with a simultaneous horizontal compression here. All right, here we have g of x equals negative square root of 3x, and we're going to try to graph it using only transformations, right, without actually sitting there and plotting points, right? So notice that the reference function is f of x equals square root of x. So if we want to graph this function, which is negative square root of 3x, that's negative f of 3x. Now, remember that this is going to, when you have negative f, right, you're applying a negative to the y value, so you're going to be reflecting, right, with respect to the x-axis. And because of this 3, remember, when you have f of 3x, you're going to be actually horizontally compressing it by a factor of 1 over k, remember? So 1/3. Now, sometimes the fact that this is horizontally compressed compared to this is a little hard to see. So let me show you on a graphing site. Give me 1 second. All right, so notice here, I'm showing you the graph of y equals the positive square root of 3x. It's a little bit easier for you to see the horizontal compression with the positive case, because then the reflection is not a big deal. It's easy, you just reflect it. Now, notice that at the same elevation 2, right, the modified graph, the square root of 3x, has a value that is an x value that's 1/3 the value of the x value for the original graph of square root of x. This is what we mean by horizontal compression, okay? And again, if you notice, it looks like a vertical what? Stretch. Horizontal compression, vertical stretch. It looks like this thing has been vertically stretched, doesn't it? Okay. So that's what we're talking about when we say that this function is horizontally compressed compared to that function. And of course, if I want to just now move it down, all I got to do is just do that, right? Once I bring in the negative, that's going to reflect it across the x-axis, okay? Because all the y's become negative y's, right? All right, so that's that. All right, here's another one. G of x equals negative 2 radical x plus 4 minus 3. Without looking further down, get a piece of paper, see if you can come up with the transformations you need to do to some reference function to get the graph of this function. First, decide what the reference function is, okay? All right, welcome back. I think you know that the reference function here is going to be f of x equals square root of x, right? So given that, we can rewrite this as, all right, for the keen-eyed among you, there was a typo which I quickly fixed. So we have f of x equals square root of x is our reference function or base function. In that case, g of x becomes negative 2 f of x plus 4 minus 3, right? So we know that to get the graph of f of x plus 4 from the graph of f of x, we have to move it 4 units to the left, right? And then because of this minus 3, we're going to move it 3 units down, right? And because of the negative, well, because of the 2, we're going to vertically stretch by a factor of 2. And because of the negative there, we're going to have to reflect with respect to the x-axis, okay? So there's several things going on here. Now, I told you a different order than you see here when I was just looking at it, but this will also work. So we vertically reflect the graph of f of x equals square root of x, then vertically stretch it by a factor of 2, then move it 4 units down, and to the left, and 4 units to the left, and 3 units down. Okay, so several things going on here, but once you get a hang of this, it becomes really easy for you. So just don't give up and hang in there. All right, so here we want to graph g of x is equal to square root of negative x. Our base function is going to be f of x equals square root of x, our reference function. So g of x, which is the square root of negative x, notice that's just f of negative x. Because if f of x is square root of x, right? what is f of negative x? Well, wherever you see x, you're going to replace it with a negative, right? Now, notice that some people look at that and they get confused. They say, you said you can't take the square root of a negative number. Well, who said anything about taking the square root of a negative number? You're just changing the domain of this function. So here we want negative x to be greater than or equal to 0. Multiply both sides by -1. So you get x has to be what? Less than or equal to 0, which is the case that you see here. So we basically have to take the graph of square root of x shown here in dashed format and reflect it across the y-axis, okay? And there we go. This is a horizontal reflection, right? The ones we had seen until now were vertical reflections. When the input is what changes from positive to negative, that's when you do a horizontal reflection. All right, the next concept we want to understand with respect to graphing techniques is understand the notion of symmetry. There are three types of main types of symmetry that we encounter when we're graphing relations, and some of which happen to be functions. Symmetry with respect to the y-axis, okay? Notice that a given x value and its opposite need to give me the same y value, right? So that's why the requirement or the check for such symmetry entails replacing x with negative x, and if doing that leaves the original equation unchanged, then the particular equation will have a graph that's symmetric with respect to the y-axis. Here's a simple, great example. Consider y equals x squared. Note that if you change x with negative x, right, instead of x putting negative x and you square it, you get back to the original x squared, which is y. So in other words, changing x and negative x left this original equation unchanged. That's why we knew this equation would have symmetry with respect to the y-axis. Symmetry with respect to the x-axis is going to require that for a fixed x value, you get two different y values, a y value and its opposite, right? So that's why changing y and negative y should leave the original equation unchanged. So here's a good example of that, the horizontally oriented parabola known as x equals y squared. Notice that if we replace y with negative y, we get quantity negative y squared, which is y squared, which is of course x. So that leaves the original equation unchanged, you see? And that's how we know, just by looking at this, that this should have symmetry with respect to the x-axis. Finally, there is symmetry with respect to the origin, and the way you can tell is this, that replacing x with negative x and y with negative I should leave the original equation unchanged. So here's a great example of symmetry with respect to the origin, the cubic function, okay? Or the cubing function, right? Is what we called it before. So we have y equals x cubed. Notice that if I replace x with negative x and y with negative y, I get negative y equals quantity negative x cubed. So negative y equals, I have a typo, that equal sign should be a minus sign. Negative x cubed, and then multiplying both sides by -1 will give me y equals x cubed. So making both of those changes will leave the original equation unchanged. That's how we know this equation would have a graph that is symmetric with respect to the origin. All right, so those are the three types of symmetry. So if we want to check symmetry with respect to the y-axis, we're going to replace x with negative x. If we want to check symmetry with respect to the x-axis, we replace y with negative y and make sure it leaves the original equation unchanged. And when we want to check symmetry with respect to the origin, we're going to do both. We're going to change x with negative x and y with negative y and see if we end up with the original equation. If that happens, then it is symmetric with respect to the origin. All right, so here we're going to test this equation for symmetry with respect to the x-axis, the y-axis, and the origin. So when we want to check it with respect to the x-axis, we replace y with negative y, right? So negative y equals x squared plus 3. And if you multiply both sides by negative 1, you get y equals negative x squared minus 3. Did it leave the original equation unchanged? No. So there is no symmetry with respect to the x-axis. How about with respect to the y-axis? Well, if we want to check symmetry with respect to the y-axis, we have to change x with negative x and see if we can get back to the original equation. So y equals, we're going to replace x with negative x. Now notice that the square of negative x is just x squared, right? Because negative 1 squared is 1. So we just get y equals x squared plus 3, right? So did we get back to the original equation? We did. So changing x to negative x didn't change the original equation. So therefore, yes, this one works. And how about with respect to the origin? Well, if we want to check symmetry with respect to 0, 0 or the origin, we have to change x with negative x and y with negative y and see if we can get back to the original equation. So y becomes negative y and x becomes negative x. So we get negative y equals x squared plus 3. So y equals negative x squared minus 3. So once again, we did not get back to the original equation. So there is no symmetry with respect to the origin. So this equation will lead to a graph that is only symmetric with respect to the y-axis, because that was the only one test that passed, okay? Next, we want to check this equation. Go ahead and pause and try it on your own, see if our answers agree. All right, so to check symmetry with respect to the x-axis, we're going to replace y with negative y, and we get x equals quantity negative y squared plus 3. Now, quantity negative y squared is just y squared, because negative 1 squared is going to give you 1, right? So we get this. So did we get back to the original equation by changing y with negative y? We did. So yes, it does have symmetry with respect to the x-axis. With respect to the y-axis, right, we need to replace x with negative x and see if we can get back to the original equation. I think you already know where this is going, but let's go ahead and carry on anyway. So we're going to replace x with negative x. The y squared plus 3 doesn't change. Notice multiplying both sides by negative 1 gives me x equals negative y squared minus 3. I did not get back to the original equation, so no, this equation does not have a graph that's symmetric with respect to the y-axis. All right, finally, to check symmetry with respect to the origin, we're going to replace x with negative x and y with negative y. So we get negative x equals quantity negative y squared plus 3. So negative x equals y squared plus 3. So x equals negative y squared minus 3. We did not get back to the original equation. So it is not symmetric with respect to the origin either. So this equation has a graph that is only symmetric with respect to the x-axis. All right, let's check this one. X squared plus y squared equals 25. You should recognize that as a what? That's a circle, and it's centered at the origin. So one would hope and expect to have all kinds of symmetry, right? Well, let's see. If you want to check symmetry with respect to the x-axis, we're going to replace y with negative y. So we get x squared plus quantity negative y squared equals 25. X squared plus, that's just going to be y squared. So we got back to the original equation. So yes, it does have symmetry with respect to the x-axis. We want to check it with respect to the y-axis. We replace x with negative x. And we get quantity negative x squared plus y squared equals 25. So x squared plus y squared equals 25. Once again, we got back to the original equation. So yes, it has symmetry with respect to y-axis as expected. And with respect to 0, 0, we're going to change both x to negative x and y to negative y. We end up with quantity negative x squared plus quantity negative y squared equals 25. So x squared plus y squared equals 25. So yes, symmetric with respect to origin as well. The origin. Okay, so obviously we expected this circle centered at the origin to have all kinds of symmetry, and in fact it does. All right, so we're going to test this one now. So to check symmetry with respect to the x-axis, we replace y with negative y. So we get negative y equals x cubed. Multiplying both sides by negative 1 gives me y equals negative x cubed. So we did not get back to the original equation, so it's not symmetric with respect to the x-axis. To check symmetry with respect to the y-axis, right, we're going to replace x with negative x. So y equals quantity negative x cubed, so y equals negative x cubed. So once again, we did not get back to the original equation, so no, it doesn't have symmetry with respect to the y-axis. And with respect to the origin, we replace x with negative x. And y with negative y. So we get negative y equals quantity negative x cubed. So negative y equals negative x cubed. Multiplying both sides by negative 1 gives us y equals x cubed. So this one works. And as expected, we knew the graph of the cubing function is symmetric with respect to the origin, right? So there is the verification. All right, so that do notice that being symmetric with respect to the origin doesn't imply symmetry of any other kind. So keep that in mind. All right, so here's some important facts about symmetry. Now, symmetry with respect to both axes, the x-axis and the y-axis, does imply symmetry with respect to 0, 0. We saw that in the case of the circle with center at 0, 0. Remember, it was symmetric with respect to x-axis and y-axis, and it did end up being symmetric with respect to 0, 0. This is a conditional. It is not a biconditional. It doesn't work the other way around. Just because you have symmetry with respect to the origin, that does not imply you have symmetry with either with respect to either axis. Okay, and we just saw that with respect to y equals what? X cubed. All right. Now, an interesting one is that if you possess any two types of symmetry, you're automatically going to possess the third one as well. Therefore, you're going to possess all three of them. The proof of a fact like this would not be difficult, and it would be a great exercise for you. And if you want to graph symmetries with respect to the x-axis, actually graphs that are symmetric with respect to the x-axis, remember, those are the ones that are going to have an upper part and a lower part. They're obviously going to be not graphs of a function because they're going to fail the vertical line test, right? So a graph symmetric with respect to the x-axis does not represent a function. Remember that. Most importantly, understand that. Remember, it's much, much better to understand and let remembering happen on its own. And it always does. Trust me on that. Another great thing about understanding is that it stays with you. When you understand something, think of anything you've ever understood in your life, right? It just stays. It's yours. See, it's kind of like when you understand something, you're buying something and making it your own, right? Whereas when you're just trying to remember and memorize, you're just borrowing, and you can only keep it for a very short period of time, and then it's gone, right? But so always go for the full purchase, right? Understand it, make it your own. All right, we've reached the last topic for the day, and that is the concept of even and odd functions. We know even and odd numbers, right? Well, functions have kind of an equivalent concept called even and odd functions. Now, a function f is said to be an even function if f of negative x is the same as f of x for all x in its domain, okay? Now, what does that indicate? That should kind of tell you something, right? That means replacing x and negative x doesn't matter, right? So that means these are going to be symmetric with respect to what? You guessed it, the y-axis. Now, why is that true? Well, look, let y equal f of x be an even function. Now replace x with negative x, right? So what do you get? You get f of negative x equals f of x, which is y. So in other words, this leaves the original function unchanged, so therefore y equals f of x is symmetric with respect to the y-axis. Of course, we're being a little loose with terminology here. We mean the graph of y equals f of x is symmetric with respect to the y-axis, okay? Now, a function f is said to be an odd function if f of negative x equals negative f of x for all x in the domain, okay? So this, of course, indicates that the graph of an odd function should always be symmetric with respect to what? The origin. Why? Because look, let y be f of x be an odd function. Now replace x with negative x and y with negative I. So what do we get? We get negative y equals f of negative x. We're replacing x with negative x, right? So we get negative y equals negative f of x, and multiplying both sides by negative 1 gives us y equals f of x. So we got back to the original, right? So therefore, y equals f of x is symmetric with respect to the origin. All right, let's go ahead and test some functions to see whether they're even, odd, or neither. All right, so we're going to determine if this particular function is even, odd, or neither. So basically, we're going to find f of negative x, and if it happens to end up being the same as f of x, then it is even. If it happens to be the opposite of f of x, it's odd. And if it happens to be neither of those, then it's neither, right? So f of negative x, that's going to be 6 times quantity negative x to the 4 minus 3 times quantity negative x squared plus 1, right? So we get 6x to the 4, because remember, negative 1 to the 4 is 1, x to the 4 is x to the 4, like that, minus 3x squared plus 1. So notice that's exactly equal to f of x. So therefore, f is even. Okay, so of course, we can pretty much stop there, because if it's even, it can't be odd. There's only one function that can be both of those, and that is, what do you think it is? Well, let's see. Let's take a look at it. Let's assume f. Now remember, we're done with this problem. This is just a side problem we're doing. Assume f is both even and odd. What does that mean? That means f of negative x equals what? F of x, because of the fact that f is even, and f of negative x is also equal to negative f of x, because f is also odd, right? So now look, both of these are expressions for f of negative x, right? So they must be equal, right? So that means this implies f of x equals negative f of x, right? Now, if we move both to the same side, we get f of x plus f of x equals 0. So 2f of x equals 0. Divide both sides by 2. What do you get? F of x equals 0. So there's only one function that can be both. And this obviously is not 0. And since it's even, that's it. It can't be odd as well. So therefore, we're done with that one. Now, generally speaking, I think you can understand that if the only powers that you have are even powers, right, you should be in good shape as far as the function being what? Even. And you can see how this was the motivation behind what? Behind the name for even functions, right? All right. Okay, how about this one? So let's take a look at f of negative x. So we get f of negative x equals 3 times quantity negative x cubed minus 6 times negative x, right? So that's 3 times negative x cubed plus 6x, which is negative 3x cubed plus 6x, right? Notice that if I factor out a negative, I get 3x cubed minus 6x. But look, this is what? That's f of x right here. So basically, f of negative x ended up being negative f of x. What does that tell you? This function is odd. And notice the only powers available here are odd powers, right? Okay, let's do another one. All right, so here we notice we have an even power and an odd power kind of mixed. So we would think this would end up being neither, right? And I think you're right if you guess that. All right, so let's look at f of negative x. That's going to be quantity negative x squared plus quantity negative x. So that's going to be negative x squared, actually positive x squared, because when you square negative x, the negative 1 squares and gives you 1. So just x squared minus x. Now, we know that this is not f of x, and x squared minus x is not the opposite of f of x either. What is the opposite of f of x? It's always good to kind of know what that is so that if you see it, you recognize it. Notice that's going to be negative x squared minus x. So it's not either of them, right? Therefore, f is neither even nor odd. All right, so that's how you handle those even and odd questions. All right, here's the very last thing we're going to do for the day, kind of a recap. Okay, so here we're given the graph of some function, right? We want to apply these transformations, right? So if I want to graph g of x equals f of x plus 3, what do I have to do? Remember, that's a change at the y level, so you're going to just move it up 3 units, right? So here, this point here was at -4, so when you move it up 3 units, should go up to what? -1. This point here will move up to 3, and just like that, see? This point here will go up 3 units, right? And this point here will also go up 3 units, and that's what happened with this one. So the whole graph, think of it as a little piece of metal, pull it up 3 units, and that's what happens. With this one, that's a horizontal shift, right? Or horizontal translation. How many units? 3 units. Which way? Left, remember? So this one you move left 3 units, and that's why you get this graph. So f of x minus 2 plus 3. So we're going to first move it 2 units to the right, right? And then move it 3 units up. So if you do that, you'll finally end up with this. And for this one, negative f of x, that's a reflection with respect to what? With respect to the x-axis. So basically, you're going to flip the whole graph. So this part obviously will go up, and this part will go down, because you're just taking the opposite of each y value, right? All right, so very important lesson in that it's going to help us with graphing throughout the term. Okay, we're going to be visiting concepts in this video throughout the term, and every time we encounter a graph, right? So make sure that you have a solid understanding of all these different transformations before you continue. All right, so you take care, and we'll see you for the next lecture.